In this video, we're going to prove the very important theorem. It states that the linear Diophantine equation, better known as ax plus by equals c, it has a solution if and only if d, the GCD of a and b, divides c. So the GCD of a and b, for there to be a solution, it must divide c. We need to prove that. Also, if xy is any particular solution of this form, then there are other solutions, and they must be in this form. They relate to the original solution or the particular solution. So this theorem, it has two parts. It has this part here, which is an if and only if proof. That is, I need to show that ax plus by equals c has a solution if and only if d divides c. And part b to this theorem is this right here. If there is a solution, then we can generate infinitely many solutions. So let's get right into the proof. Okay, so let's suppose that ax plus by equals c. Well, since d equals the GCD of a and b, that implies d divides a and d divides b. But that implies that d divides any linear combination of a and b. Well, I want it to be that linear combination. Therefore, d divides ax plus by, but that means d divides c. Okay, so I started off with ax plus by is the solution, and I concluded that d divides c. Now we go the other way. I'm going to show that d divides c. I'm going to start off with d divides c, and I'm going to show that ax plus by equals c. Okay, so assume that d divides c. That means that c is some multiple of d. But c is equal to m times d. But d is, say, ax plus by. This implies, if you write it cleverly, when you distribute, this is a times mx plus b times my. That is, c is a linear combination, is a times an integer plus b times an integer. So linear combination, this here is a linear combination of a and b. Ooh, and it equals c. That is, I found the solution to a times big X plus b times big Y. That is, I found X and Y so that C is a linear combination of A and B. That's all I wanted to show. So what's in blue on top has been satisfied. Got it. Now we need to work on what's in red. Suppose that x0, y0 is any linear any solution to ax plus by. And give me one moment, please. Okay, so suppose, I want to use the exact wording. They said x0, y0. Suppose ax0 plus, let me say it more formally. Suppose x0, y0 is a solution to ax plus by equals c. That is ax0 plus by0 equals c. Now suppose that x prime y prime is another solution to ax plus by equals c. And I want to show that x and y, x prime, y prime, is in this form, where x0, y0 is a solution. Okay, now, if both this and that are solutions, we have that ax0 plus by0 is c, but c is also ax prime plus by prime. That is, this equals that. Bringing the a's to one side and the b's to the other side, we get that a times x0 minus x prime is equal to b times, b times y prime minus y0. y prime. Okay, actually, it should say that. Okay. Now, we know that D divides A and D divides B, because D is the the greatest common divisor of A and B. That implies that A is some multiple of D. That came from here, and from here we have B is some multiple of D. Okay. So this equation becomes A, which I'll write as RD, times x0 minus x prime, is equal to B, which is SD, times y prime minus y0. Divide both sides by D. Now, note that the GCD of R and S is 1. We proved that. If the GCD of R and S are relatively prime. Okay, so what we have is distributing. We have, well, let's not distribute yet. We have that R divides S times y prime minus y0, because this, here it is a multiple of R, is R times that. But since R and S have absolutely nothing in common, this here must imply that R divides y prime minus y0. But that implies that y prime minus y0 is r times t. Similarly, s divides r times x0 minus r prime, because this is a multiple of s. This is some multiple of s. Well, that implies that r times x0 minus r x1 is some multiple of s. Well, let me back up. That's not untrue. But let me do the same thing I did above. R and S have no common divisors other than 1. So that implies S must divide the other factor, namely x0 minus x prime. Well, that implies that x0 minus x prime is a multiple of S. Say S times t. So now we have this relationship between x0 and x prime, and above we have a relationship between y prime and y0. They're call this equation 2 and this equation 1. Equation number 2 tells us that x prime is equal to x0 minus st. And equation 1 tells me that y prime is y0 plus rt. Couple of more lines. X prime is x0 minus any way of writing s times t, and y prime is y0 plus any old way of writing r times t. But up here, that tells us that r is d over a, and this tells me that s is b over d. So s is b over d, and r is a over d. Now, I claim that this here is a solution. Well, we know that ax0 plus by0 is c. Let's see if a times x prime plus b times y prime also equals 0. Well, it's a times this new way of writing x prime, namely x0 minus b over d times t, plus b times y prime, where that's y prime, plus a over d times t. We do get ax0 plus by0. Well, that's clearly c. But we have other stuff. We have to take away ab over dt, and we have to add ab over dt. Ooh, look at that. That turns out to be 0. So x prime, y prime is another solution. And it's in this form, just like we said it should be in. That completes this proof. It's a very important proof. So, just to be clear, t is any integer. So, we have an infinite number of solutions. Just pick different values for t. Of course, the value that you plug in here for t has to be that value of t. But for that one particular value of t, you get one answer. But there's infinitely different number of values that you can use for both of those t's. If you just love videos like this where we prove theorem after theorem lemma after lemma, corollaries after corollaries. Sounds pretty simple to me. Subscribe to my channel, like my channel, leave a comment. See you guys in the next video, and always watch and learn.